Okay, now let's talk about dialysis. Dialysis is the diffusion of substances other than water through semi-permeable membranes. Okay, so if you have, we're talking about other molecules now, and if the concentration is less here than other smaller molecules, and if this is a semi-permeable membrane, these molecules will diffuse over to here, and that's dialysis. Okay, so as long as these molecules are not water molecules, so these could be glucose, waste products, and so on. Okay, so it's the diffusion of substances other than water. Okay, through semi-permeable membranes. So these membranes are permeable to these smaller molecules. Small molecules are usually involved in dialysis since membranes tend to be impermeable to larger molecules. So generally these are smaller molecules. Reverse dialysis, also called filtration. So reverse dialysis would involve moving of these molecules from lower to higher concentration. Okay? And that's called filtration. Occurs when the pressure on the low concentration side is large enough to reverse. So what you can do is you can make these molecules flow from here to there if the pressure here is higher. Okay, so that's a typo in the textbook, and be careful. Okay, so reverse dialysis, also called filtration, occurs when pressure on the low concentration side is large enough to reverse the normal direction of dialysis. Kidneys use dialysis or osmosis and active transport to remove waste products from the blood and maintain its proper balance of fluids and electrolytes. So we'll talk about the kidneys. Okay, so here is a nephron, basic unit of a kidney. So here is the glomerular capsule. Okay, so here's capillaries. And so waste, so the job of the kidney is to get rid of waste through here, through the nephron. Okay. The basic kidney unit is a nephron. Blood circulates through the bundle of capillaries that's enclosed in a small membrane sac. So there's a membrane sac called the Bowman's capsule. Substances removed from the blood must cross two membranes. Okay. So the transport process is reverse dialysis caused by arterial blood pressure. Okay, so the concentration of waste and everything here is smaller than inside the nephron, and the higher pressure moves the stuff against the concentration gradient. Okay, so the transport process. Okay, so in the case of the kidney, the concentration here is smaller, and so higher blood pressure in the capillaries transports the waste products out. But the higher pressure also transports the good stuff out. Okay, so let's say the goods. Okay, so it transports the good stuff out as well. Okay, so the higher pressure here transferred the bad stuff and the good stuff out, and so you have to reabsorb the good stuff. Okay, so we'll come to that. Okay, so substances removed from the blood must cross two membranes. The transport process is reverse dialysis. Reverse dialysis is meaning you're going from a lower concentration to higher concentration, caused by arterial blood pressure. Only blood cells and large molecules such as proteins are left behind. The substances filtered out of the blood then move into a drainage tube. So again, there's the drainage tube, and you see you filtered out good with the bad, and all the glucose is reabsorbed. 99% of the water is reabsorbed. 98% of the sodium is reabsorbed. 94% of the potassium is reabsorbed. Ammonia, 20% of the creatine is reabsorbed. Urea, 40% of urea is reabsorbed, 88% of uric acid is reabsorbed, and then all the rest goes away. So again, to push out the waste, you're pushing out the good stuff as well. To push out the waste, you're pushing out the good stuff as well. Okay. And then you have to reabsorb the good stuff. So the waste is the red stuff, the good stuff is the green stuff. You're pushing out the waste. Your goal is to push out the waste, but you're pushing out the good stuff as well, and then the good stuff has to be reabsorbed. So the substances filtered out of the blood then move into a drainage tube where many are reabsorbed into the bloodstream. Active transport is responsible for much of the reabsorption. So you have to spend energy to reabsorb all the good stuff. Okay? But the energy you're spending is less than what you're getting from reabsorbing it, so your body does that. So the net effect of the two-step process of filtration followed by reabsorption is to rid the body of waste product while maintaining a proper balance of electrolyte, water, and so on. So kidney failure can cause high blood pressure. So if your kidneys are not functioning properly, they're not getting rid of the waste, then what your body does is it increases blood pressure so you can get rid of the waste more efficiently. Okay. But then high blood pressure causes other problems. Okay, so kidney failure can cause high blood pressure. If filtration slows or stops in the glomerulus, the kidney emits a hormone called renin that causes blood pressure to rise, so the filtration can recommence. Unfortunately, high blood pressure has many ill effects and cause capillaries in the glomerulus to burst. Okay, so if filtration slows down, the body increases blood pressure, but high blood pressure has consequences. Any substance that causes increased urine output is called a diuretic. Okay, so what happens is this water has to be reabsorbed. 99% of the water has to be reabsorbed. But if the concentration of water, so generally if the concentration of the water in the blood is less than here, then water is easily reabsorbed. But if there is molecules here that decrease the concentration of water, and if that concentration is the same as decrease the concentration of water, and then the absorption of water is less efficient. And so if you have molecules that are here and the concentration of water is decreased, this water cannot be reabsorbed, and then that water goes up. You're excreting that water. Okay. Any substance that causes increased urine output is called a diuretic, and that's because you're not reabsorbing the water. Some of these work by altering the amount of water reabsorbed in the drainage tube. They penetrate the glomerulus and Bowman's capsule, but cannot be reabsorbed in the drainage tube. So these diuretics go across the Bowman's capsule, but they cannot be reabsorbed. The presence of such a molecule decreases the concentration of water in the tube and its reabsorption, resulting in greater amount. So diuretic molecules come across here, but they're not reabsorbed, and so they make reabsorption of water difficult as well, and so you're urinating more. So one symptom of diabetes is unusual thirst and frequent urination. Diabetes victims ineffectively utilize glucose, and its concentration rises in the blood. So they have high concentration of glucose in the blood. This in turn causes an excessive amount of glucose. So there's high concentration of blood, the higher pressure there, dumped a whole bunch of glucose here, and it's hard to reabsorb all this glucose. And that glucose is a diuretic, and so you're urinating more. This in turn causes an excessive amount of glucose to pass through the glomerulus and Bowman's capsule into the proximal convoluted tubule, which is where it acts as a diuretic. Okay, you have too much glucose in your blood as a diabetic patient. Too much glucose gets in, you can't absorb this glucose, which acts as a diuretic. So active transport is the movement of ions or molecules across the cell membrane into a region of higher concentration. So active transport is transporting material from lower to higher concentration. And this requires energy. Okay, so when you absorb nutrients and so on, you need active transport. So is the movement of ions or molecules across the cell membrane into a region of higher concentration, assisted by enzymes and requiring energy. Okay, so this process requires energy. And active transport is essential for various physiological processes such as nutrient uptakes. So when you're taking in nutrients, even the concentration of nutrients outside is smaller and concentration of nutrients is higher here, you still don't want to let go of any nutrients. So you're using active transport. So for instance, glucose being reabsorbed here. Okay. So such as nutrient uptake, so you use active transport such as nutrient uptake, hormone secretion. So if you want to secrete hormones to the outside from a cell, even though the concentration is higher, you still want to keep pumping out hormones. And nerve impulse transmission. And during nerve impulse transmission, you will there's ion motion across the neuron wall, and so potassium and sodium ions move into and outside the neuron. Okay, and then when you want to reset, then you have to pump back sodium ions outside, and you're pumping them back against a gradient, a concentration gradient, and that's active transport. Okay. Unlike passive transport, which uses kinetic energy and natural entropy of the molecules moving down a gradient, active transport uses cellular energy. So active transport uses cellular energy to move them against a gradient, polar repulsion or other resistance. So so active transport is usually associated with accumulating high concentrations of molecules that the cells need. Okay, so you need such as ions, glucose, and amino acids. So even though the cells will have a higher concentration of this, you still want to keep absorbing this stuff from the outside. Okay, and then you have to use active transport. So example include the uptake of glucose in the intestines in humans and the uptake of mineral ions into the root cells of plants. So the transport processes at cellular level: diffusion, osmosis, and reverse osmosis, dialysis and reverse dialysis, which is filtration, are all passive in nature. The driving energy for passive transport comes from molecular kinetic energy or pressure. Okay, so those are all passive. Active transport involves use of energy. Okay. Okay, so there are known instances in which substances move in the direction where existing pressures are insufficient to cause reverse osmosis or reverse dialysis. In these instances, active transport must be taking place, which means that living membrane expend their own energy to transport substances. Active transport can also aid ordinary osmosis or dialysis, and explains why some transport proceed faster than expected from osmosis or dialysis alone. So we saw that organisms need to transport substances from region of low concentration to higher concentration. Okay, and then active transport is involved. So active transport is very complicated, and only now we are starting to understand it. And even now, a great deal can be said of what happens in the active transport, but not as much can be said about why it happens. The reabsorption phase of the kidney nephron is an example of active transport. So all this material being reabsorbed in the kidneys is an active transport process. Also in red blood cells, the concentration of potassium inside the red blood cells is about so inside a red blood cell, the potassium concentration is 20 times higher than outside, whereas the sodium whereas the blood plasma surrounding them has about 20 times higher sodium as potassium. Sodium concentration is outside is higher than inside, and to maintain this concentration difference, you use active transport. So potassium wants to diffuse out, and you got to keep bringing potassium back in. Sodium wants to diffuse in, you got to keep sending it back out. Active transport maintains this against the tendency of dialysis to transport sodium into the cell. Okay, so sodium wants to come into the cell, and potassium out of the cell. Okay, so this is a red blood cell. Active transport is extremely important in nerve cells as well. Now we'll come to the physics of respiration. Okay, so again, so here is a resting lung. Okay, so the pressure outside is 1 atmosphere, and the pressure inside the lungs is 1 atmosphere as well, and so the gauge pressure is 0. So now there is no motion of air. Now if you want to breathe in, you have to decrease the pressure inside the lung. Okay, and so the diaphragm, okay, so now, so the lungs contain the many alveoli. So I'm drawing one alveoli. So think of the alveoli as a rubber balloon. So the rubber increases the pressure here. Okay. Okay, so if the pressure of just the so right now, okay, so the pressure inside the lung is 1 atmosphere, meaning the gauge pressure is 0. Okay, now when you breathe in, the diaphragm lowers, so the surrounding cavity, by the way, so right now the intrathoracic pressure is minus 3.44 minus 3.4 centimeters of water. Okay, so the pressure here is given in centimeters of water. Okay, that means so outside it's 3.4 centimeters of water. Okay, and by the way, 10 meters of water is 1 atmosphere. Okay, so this is 1 atmosphere, so 1 meter would be 10%, and 10 centimeters would be 1%. So this is about 0.3% of atmospheric pressure. Okay. So what this means is in the intrathoracic cavity, you have negative pressure. This elastic balloon provides 0.34% of pressure plus 0.34%. And so here the net pressure is 0, which balances the atmospheric pressure. Okay, so when you want to breathe in, what you have to do is you have to reduce this pressure. So when you breathe in, your thoracic cavity expands and the interthoracic pressure decreases to that. The pressure inside your lungs has decreased to minus 0.27 centimeters of uh, water, and so air flows in. Okay, so you've reduced the pressure inside your alveoli by decreasing the surrounding pressure. Okay, so air flows in. Now there's more air molecules there, and so when the diaphragm compresses, now the pressure inside the alveoli is greater than atmospheric pressure, and the air will flow out. Okay, so when you want to breathe in, when the pressure inside, the net pressure inside the alveoli is the same as atmospheric pressure, no air flows in or out. So to make air flow in, you have to decrease the pressure inside the alveoli, and you decrease it to that value by increasing the volume of your intrathoracic cavity. Okay, so there's a couple of things that happen. The diaphragm lowers and your rib cages expand as well to reduce the pressure of the intrathoracic pressure from minus 3.4 to minus 8 centimeters of water. So the respiratory system exchanges again. The respiratory system's most important function is to oxygenate blood and to remove carbon dioxide from it. Yeah. The respiratory system also exchanges heat with the environment by the evaporation of water and by forced convection. So a lot of heat is also lost by evaporation of water in the breath, in your breathing. Okay, so remember, every time 1 gram of, we learned this, when 1 gram of water vapor evaporates, it takes away 540 calories of heat. Okay, so air flows into the lungs when pressure in them is less than atmospheric pressure. So right now it's atmospheric pressure, meaning gauge pressure is 0. When the diaphragm is lowered, the intrathoracic pressure decreases and the pressure inside the lungs decreases to that, and now air can flow in. Okay, so it's that much below the atmospheric pressure, and now you have more air, and when you compress your thoracic cavity back to the original size, the pressure inside is above the atmospheric pressure and air flows out. Again, flow rate is proportional to the pressure difference divided by the resistance. Okay, so so in this case, the pressure difference is 2.7 centimeters. Outside pressure is higher than the pressure inside the alveoli by that much, and air flows in. And when you're exhaling, this pressure is higher than the atmospheric pressure by that much. Okay, and air flows out. The body changes pressure in the lungs by increasing or decreasing the volume surrounding the lungs. During inhalation, the lungs expand by muscle action and the diaphragm and rib cage. Okay, so the diaphragm and rib cage help in expanding this intrathoracic cavity, and the pressure drops. So the diaphragm is a sheet of muscle lying below the lungs. When relaxed, it has an upward curvature. So this is a relaxed diaphragm. And when contracted, so when the diaphragm contracts, this is its configuration. It moves downward and expanding the lungs. At the same time, certain muscles in the upper body also contract and increase the size of the rib cage, further decreasing the volume of the lungs. Again, your goal is to reduce the intrathoracic pressure from minus 3.4 to minus 8 centimeters of water. During exhalation, the muscles relax and the diaphragm and ribcage return to their original shape. Okay, so during exhalation, they return to the original shape. Now the pressure in the alveoli is higher than the atmospheric pressure and air flows out. Air is thus pushed out of the lungs. No muscle action is required to exhale, but it may be used to speed exhalation by forcibly contracting the rib cage. Again. Cohesive and adhesive forces in the lungs, in and around the lungs, play important roles in the breathing mechanism. The lungs are attached to the cell wall by liquid contact, that is, by adhesive forces. The lungs are pulled open by these adhesive forces when the rib cage expands and the diaphragm moves downward. The pressure in the region between the lungs and the chest wall rises and falls but remains negative. If intrathoracic pressure outside the lungs is negative during normal breathing, how does pressure inside the lungs become positive or cause exhalation? The answer is that the surface tension in the alveoli make the lungs elastic like an inflated balloon. Intrathoracic pressure must in fact be negative to keep the lungs expanded. So for instance, if there is a injury to the chest cavity and this vacuum leaks out or air leaks in and you don't have this negative pressure, your lungs will collapse. Okay. Any injury that allows air into the chest cavity increases pressure to atmospheric pressure and forces the lungs to collapse due to their surface tension. This condition is called pneumothorax, and it can be caused by an accident or by surgery, or may occur spontaneously. Air is suctioned out of the intrathoracic region to remedy severe pneumothorax, although the body can slowly reabsorb the air in less severe cases. So gas transferred into our blood is a primary function of the respiratory system. So there are the alveoli and venous blood coming in, and oxygen exchanges happen, and blood is going back to the heart. Oxygenated blood is going back to the heart. The breathing passage in the lungs branch into smaller and smaller tubes ending in alveoli, where the exchange of gases take place. The hundreds of millions of alveoli are each about 200 micrometer in diameter. So the alveoli are 200 micrometer in diameter and have walls about 0.4 micrometers thick. So fairly thin walls. Blood passing through the capillaries adjacent to the alveoli exchange gases with the air. So this blood passing exchanges gases with the air in the alveoli by diffusion through the capillary and alveolar walls. So carbon dioxide goes into the alveoli, oxygen comes into the blood. Diffusion of gases between air in the lungs and blood proceeds in the direction of high to low concentrations. And the rate of diffusion is greatest when the difference in concentration is greater. The actual rate of exchange is greatly affected by the presence of hemoglobin in the blood. Hemoglobin has an affinity for oxygen, and its presence allows blood to carry far more oxygen than it could otherwise. The rate of exchange also depends on blood acidity and presence of carbon dioxide and temperature. Yeah. So, relative concentration of oxygen and carbon dioxide determines the direction of gas transfer. Partial pressure of the gas is a good proxy for concentration. About 20% of oxygen, atmosphere molecules are oxygen, and so the partial pressure of oxygen is thus 20%. So if atmospheric pressure is 760 millimeters of mercury, 20% of that is about 150 millimeters of mercury. So every time you breathe in, the pressure of oxygen in your lungs is 150 millimeters of mercury. So if you want to absorb oxygen, the pressure of oxygen in your blood has to be less than that. So the oxygen pressure is that. If the air in the lungs has well, it turns out that the actual pressure of oxygen in your lungs is about 105 millimeters of mercury. And in the blood, it's 40 millimeters of mercury. So you see, in your lungs, the partial pressure of oxygen is much higher than in blood. And so oxygen goes into the blood. Okay. The partial pressure of oxygen in the lungs is only 105 millimeter rather than 150, because air in the lungs is only partially replaced with each breath. Okay, so you sort of have stale breath in your lungs all the time. Similarly, the partial pressure of carbon dioxide in the lungs is greater than in the atmosphere. And so the partial pressure of carbon dioxide in your blood is greater than in the atmosphere. Okay, so this should be in the blood. So I'll fix that. Yeah. Oxygenated blood from the heart travels through the arteries to the capillaries, where it's transferred to the cells having lower oxygen concentration. Oxygen poor blood travels back through the veins to the lungs, where the process begins again. Okay. So anyway, in the lungs, the gases are exchanged via diffusion. Okay. All right, so we saw how pressure and diffusion work in your body to exchange nutrients, to expel waste products, and so on. Okay, so your body uses passive and active diffusion at the cellular level, and when you want to transport material large distances, you have other kinds of mechanisms, circulatory system, and your lungs and all for oxygen exchange. Diffusion works only at the cellular level. Okay, all right, that ends this chapter, so we'll stop now.